Hello all, welcome to my course on methods of adhesion measurement, theory and practice. We are at lecture 41 today and we are discussing about a thin layer of elastic adhesive confined between two parallel plates, rigid parallel plates. And here are those references. So, we are discussing the topic from this particular reference 39 to 41, and this is the summary of the last lecture. In essence, we discussed about this elastic film which is confined between these two rigid plates. It is bonded to the bottom substrate and in the top surface it is in no slip contact. Okay. So, in absence of slippage. So, we will discuss today about where we had stopped from the last class. So, here in essence we had derived this stress equilibrium relations and we have derived the solution for this equation along with this volume strain, okay, this relation basically compressibility relation, and then we solved for u and w. So, u and w, these are the dimensionless deformations along the x direction and the z direction respectively. Remember that we are solving this problem in plane strain approximation. So, that is in x direction is this direction and the z is in this direction and y is in this direction. So, we are solving this problem in the plane strain approximation, that you have to remember. Now, we have here this is the equation. So, yeah, so we solved these problems and finally, we derived this expression in terms of this constant P1, and over here this is the pressure that is being applied P here like this. So, we are at this particular state and we need to now go beyond that. So, now, so this delta minus 2 P1 cos of cos hyperbolic square root of C1 into capital S. So, C1 is also a constant that we have obtained integration constant earlier in the last lecture. So, here at the edge of the sandwich film at x is equal to plus minus L by 2. So, x is equal to plus minus L by 2, the film is open to atmosphere. So, that means this is the film and this is bonded to this between two parallel plates. So, this is L by 2 here, and at this point, okay, at this point it is pressure is equal to 0. So, the pressure P is equal to 0 here, and so therefore, this is capital P is equal to 0, and so therefore, delta minus 2 P1 cos hyperbolic square root of C1 and plus minus. So, let us say plus L by 2. So, this is equal to minus or so this is equal to 0. So, therefore, we have here P1, okay. So, we obtain an expression for that. This is equal to delta by 2 cos hyperbolic square root of C1 into L by 2. So, this solution we can obtain, and so therefore, we can substitute it in the expression over here. So, let us substitute that. So, it is delta minus 2 into this is P1 is delta by 2 into cos hyperbolic, it is square root of C1 into L by 2. Okay. This is equal to minus of P by capital K. So, this 2 and 2 gets cancelled. So, what we have here is delta into 1 minus this is 1 by this is cos hyperbolic square root of C1 into L by 2. So, this is equal to minus of P by K. So, P by K you have, and so now this is one point. So, this is at x L by 2. So, at capital X. So, here this is one point that needs to be taken care of. So, capital X, okay, is actually x by L. So, this is actually plus minus 1 by 2 therefore. So, this is actually plus minus 1 by 2 that has to be taken. So, here not L, I should take it 1 here. So, this is the solution. So, finally, one can get here. So, therefore, this is minus k by 2. So, this is okay. Yeah. So, now finally, one will get from P1. So, P1 is equal to this. So, delta minus this is 2 P1. So, there is cos of this is cos, I should have written that cos of square root of C1 into capital X. Yeah, this I missed. So, here this is delta. So, it is cos hyperbolic of C1 square root of C1 into x. Yeah, from here one gets this. So, here this is 2 into P1 into cos. Yeah, so this is now correct. So, we obtain here this, and so therefore, P minus P we get here like that. So, let us get it over here. So, minus P is equal to, this is capital K into delta into 1 minus, this is cos hyperbolic square root of C1 into x divided by cos hyperbolic square root of Q1 by 2 here like this. So, this is K. So, now the total force that needs to be applied, that is applied is equal to force is equal to minus P into d of x. So, minus P into d of x, and that is applied from minus L by 2 to plus L by 2. And so, this is the total force that is being applied per unit length. Remember, this is the per unit length along the y axis. So, this is the force per unit length along the y axis. So, one is to integrate this, and remember this cos hyperbolic function on integration will be the sine hyperbolic. So, I have done it over here. So, this is minus k into, so here so since it is x is varying from minus L by 2 and capital P is in terms of capital X dimensionless quantity. So, therefore, here this L has come over here and the integration is being done from minus 1 by 2 to plus 1 by 2, and this since it is symmetric. So, it is 2 here. So, integration is done between 0 to half. So, please take care of that. So, 0 to this is 1 by 2 and minus P. So, it is capital K into delta. Let me take delta out. So, delta out here, and 1 minus this is cos hyperbolic square root of C1 into x by cos, this is square root of C1 by 2 into d of x. So, this is equal to 2L, and this is delta into k into half. So, this is let us say delta into k, this is capital X. Now, here it is half over here. So, it is half and then minus, and now here this is cos. So, it will be 1 by square root of C1 into sine hyperbolic square root of C1, and here this is x, let us put it like that, and this is cos of square root of C1 by 2, and this is 0 to 1 by 2. So, 1 by square root of C1 comes because of the integration. Now, that is fine. So, this is equal to therefore 2L delta into k. So, k here is, remember, that is the bulk modulus, and then this is half and minus. So, 1 by square root of C1 here, and this is half goes. So, it will be sine hyperbolic square root of C1 into 1 by 2 by cos hyperbolic square root of C1 by 2. So, this will be tan hyperbolic square root of C1 by 2. So, here now I can take it outside. So, it will be here L into delta into k into 1 minus, let us say this is tan hyperbolic square root of C1 by 2 by square root of C1 by 2. So, this is the expression for the force per unit width of the plate on the film. So, the per unit width. So, width is measured along the y axis in which we have this plane strain approximation. So, now we have this expression. So, we can actually write tan hyperbolic function something like this. It is a series expansion, can be written as x minus x cube by 3 plus 2 x to the power 5 by 5. So, therefore, you see tan hyperbolic of x divided by x. So, this quantity as I have written it in the previous slide. So, this is equal to KLW 1 minus this is tan hyperbolic square root of C1 by 2 by square root of C1 by 2 here. So, here this square root of C1 I will write it as x in essence. So, here this is equal to 1 minus this is x square by 3 plus this is 2 x to the power 4 by 5 dot dot dot. So, 1 minus, so therefore 1 minus tan hyperbolic of x divided by x, this will be 1 minus 1 plus this is x square by 3 minus 2 x to the power 4 by 5 plus dot dot dot. So, this 1 gets cancelled over here. So, what we have is x square by 3 minus 2 x to the power 4 by 5 and like that. So, therefore, this f is equal to k l delta into 1 minus this quantity. So, this is equal to x square by 3 minus 2 x square, sorry, 2 x to the power 4 by 5, let me write it properly, and plus like that. So, here now what happens? So, here as you can see this x, now what is this x is square root of C1 by 2. So, x is equal to square. So, now C1, so what is the expression for the C1? So, that we have derived in the last lecture C1, and what will come out to be is that C1 will come out to be too small, okay, too small in the sense that we can actually neglect these higher order terms. Okay. So, therefore, we will have in essence k l delta. So, these are higher order terms which we will neglect actually, higher order terms negligible. So, we will neglect this term, and in we have is k l w and x square by 3, and x square is square root of C1 by 2. So, it is C1 by 4. So, we have k l w into C1 by 12. This is the answer that we have. This is answer that we have here derived. Now, C1 is equal to this 24 1 minus sigma into 1 minus 2 sigma by epsilon square, and epsilon square, if you remember, this is equal to h by L, epsilon is h by L, right, and square, remember that. So, therefore, here I will neglect, as I already said, the higher order terms. So, here therefore, because this term is already quite small in that way. So, here therefore, f is equal to k l delta into 1 by 12, C1 is equal to 24 into 1 minus sigma into 1 minus 2 sigma divided by epsilon square. So, epsilon square, let me write it directly, h over L. So, L was the length, okay, along the x direction, and h is the thickness of the film, remember that. So, this is this, and delta. So, in the delta I will write it as delta by h, small delta by h. So, capital delta, this is the dimensionless deformation that has happened, right. So, like that. So, now this is k. Now, I can actually write in terms of k also I can expand. So, k is 2 mu by 1 plus sigma by 3 into 1 minus 2 sigma. Okay, let me write it. So, k is equal to 2 mu into 1 plus sigma by 3 into 1 minus 2 sigma. Is that correct? 2 mu 1 plus sigma 3 into 1 minus 2 sigma into this is, let us say I put it directly 2 here, delta by h here, and then here it is 2 into 1 minus sigma by 1 minus 2 sigma by h by L whole square. So, therefore, this 2 is there. So, now this 1 minus 2 sigma into 1 minus 2 sigma gets cancelled. So, what I have now is 4 by 3 mu 1 plus sigma by 1 minus sigma. So, that is 1 minus sigma square, 1 minus sigma square. So, 4 mu by 3, 1 minus sigma square here and delta here, and this is h, delta by h, and here it is 1 upon h by L whole square. So, this is the kind of expression that I have. Now, so here it is like this. So, finally, f by L into delta into mu. So, that I will get this kind of. So, the compressive, so this is the expression that I get. So, the compressive load on plate, so that will be equal to compressive load on the plate, so that is equal to L into delta. So, it is F, remember that it is per unit width. So, width I can write it as omega. So, remember that this f into width w. So, therefore, it is equal to 4 by 3 1 minus sigma square, okay, and here it is L cube delta mu and 3 h cube into w here. Okay, so, that will be the expression. So, f 4 by 3 here 1 minus sigma, this L cube delta, okay, and mu and omega or w. So, that is the width of this film, and this 3 h cube and a 3 into h cube, and for an incompressible film. So, therefore, f will be equal to, so this incompressible film sigma is equal to half. So, it is 1 by 4 3 by 4. So, that gets cancelled. So, here I have L cube by h cube and delta into mu into omega. So, this is the expression that I get. So, this is, so you see this means that this is delta and delta into this is mu and this is omega by h by L whole cube. So, h by L, that is a kind of confinement parameter. So, to the extent that film is confined, okay, and so therefore, this f, okay, that increases with decrease in this confinement parameter value. So, as h by L decreases, so h by L, okay, as it decreases, confinement of the film increases, confinement of the film increases, okay. So, confinement film increases means that you require larger force, okay, to deform it perpendicular, okay, perpendicular to it you will need larger force. So, one can actually think of this quantity, this is this quantity, let us say this quantity, okay, kind of spring constant. So, f into this is spring constant, okay, let us say k, usually the way spring constant represent k into delta, okay. So, that is the way it is. So, you see that the spring constant will increase for a thinner film, that is what it means, actually more confined film. Now, let us take a problem. A thin elastic film, Young's modulus 3 megapascal, Poisson ratio 0.5, thickness 500 micron. Okay. So, Young's modulus is 3 megapascal. So, mu shear modulus we know that it is E over 2 into 1 plus sigma, and so therefore, it is 1 megapascal here. Thickness 500 micron. So, compressive strain, okay. Now, dimension, okay. So, 30 it is bonded to rigid substrate while being compressed by a rigid substrate from the top. Considering the no slip boundary condition at the film substrate interface, the plane strain condition and plane strain condition obtain the force that needs to be applied to compress the film by 2%. So, compressive strength is 0.02. So, this is actually equal to delta by h, remember that. So, the delta, so delta is the extent to which it has been compressed and h is the film thickness. So, the compressive strain is 2%, that is delta by h. So, this gives delta is equal to what? 0.02 into h. So, thickness of the film is 500 micron. So, 500, and let me use SI unit. So, it is meter over here. So, this is 10 to the power whatever it is. So, this is 5 10 to the power 2, 5 10 to the power minus 4, 10, and this is 10 to the power minus 4, and this is 10 to the power minus 2, 10 to the power minus 6. So, this is actually 10 to the power minus 6 meter. So, 10 micron, 2%. So, 500 of 2%. So, 2 is 1000. Yeah, I think that is fine, 10 micron. Lateral dimension of the film, so that is L. So, L is equal to actually 2L. So, L is should be a lateral dimension is 30 millimeter. Okay. So, compression lateral dimension 30 millimeter, right? I think that is what I have taken, 30 millimeter. 30 millimeter I have taken. Actually, I should take L is equal to 15 millimeter. Actually, it is 2L. So, this is so let us do it. Actually, this should be L is equal to 15 millimeter, not 2 millimeter, because L is 2L is the lateral dimension of the film. In the way that I have drawn this, I have considered this film area. This distance is L by 2 here. So, L is actually okay 30 millimeter, that is fine. So, this is equal to 30 into 10 to the power minus 3 meter. Compressive force that we applied, so that I have just derived compressive force. So, it is F is equal to L 4 into 1 minus sigma square. So, it is actually sigma is half. So, therefore, it will be incompressible. So, it is quantity F by L W mu is into, so let me write it, F by L W mu. So, F is equal to L delta mu into L square by H cube. So, let us do it like this, into 1 by H by L whole cube. So, F is equal to delta. So, here F is equal to, this is delta into mu into 1 by H by L whole cube, right, like this. So, here remember that whenever we do that, we also do the dimension, just check it that if everything is fine. So, looks like here everything is fine. Okay. So, here it is like this. So, now this is equal to delta. So, delta is 10 micron. So, 10 into 10 to the power minus 6 and mu is 1 megapascal 10 to the power 6 into inverse H by L. So, thickness of the film is 500 micron. So, it is 500 into 10 to the power minus 6 and this is 30 millimeter. So, 30 into 10 to the power minus 3, this many whole cube. So, this is the kind of force that needs to be applied per meter width of this particular film, remember that. So, it is Newton per meter. Okay. So, therefore, whatever this quantity comes, we have to see. So, now this gets cancelled over here and this is 50 by 30 whole cube 500. So, this is yeah. So, I think one can do it. I did not do it here. Achha, so, I did not find out, but you can find it out, the final value. Achha, final value comes over here. So, that is equal to, so actually I have changed this Poisson ratio point, no, actually it is 0.5, I had taken it earlier, 0.5. So, it should be 0.5 only, 0.5 here. Huh? So, let us take it 0.5. So, 0.5. So, do the calculation with 0.5 only and it will come out to be somewhat larger. Now, what is the strain energy? Obtain also the strain energy per unit length of the film. So, the strain energy stored in the film is can be written. So, F has to be expressed in terms of delta here. So, the way I have expressed it over here. So, let me put it 4 into 1 minus sigma square 0 to delta, this is 4 into 1 minus, this is sigma square by 3 and this is delta into mu into inverse, this is H by L whole cube and this is d delta. So, this gives 4 into 1 minus sigma square by 3 and this is mu here, this is H by L whole cube and this delta is equals to delta square by 2, like this. So, this is the elastic energy that remains stored. Okay, that is the energy that has been spent by this external load. So, that is the energy that gets stored in the strain energy that gets stored in the film. So, that is the way it is. So, here this is 0.5 I will take. So, therefore, it is 4. So, this gets equal to 1 and this is 10 to the power 6. So, this quantity for incompressible material, okay, will be equal to 1 because it is half. And so, this is 10 to the power 6, mu is 10 to the power 6 and this H by L. Again the same thing, confinement you can find. So, H is 500 micron 10 to the power minus 6 divided by L. So, L is 30 millimeter I have said, 30 into 10 to the power minus 3 and this is cube into delta square by 2. So, delta square by 2. So, delta is, we have found out 10 micron. So, 10 into 10 to the power minus 6 whole square by 2, this many, this is this many Newton meter per meter. Okay. So, because Newton meter is the joule and this is per unit width. So, the unit here is Newton meter per meter. So, please be careful about that. So, this is the unit. So, you can now work out the using your calculator and it will come out to be about this quantity. Remember that this I have calculated with using Poisson ratio 0.48. So, you have to correct it for 0.5 and you have to see. So, it will come out to be a little larger. Yeah, that is okay. Yeah. So, so far so good. We have considered an incompressible elastic film and we derived all the equations for equations for what? For amount of the load that needs to be applied to attain certain amount of strain, longitudinal this strain along the thickness coordinate. So, that we did. So, now we will like to consider that this film is an incompressible film. Okay. So, for an incompressible material we will write the stress equilibrium relations slightly differently, and these are written something like this. This can be done. So, something like this. So, this is the expression for the stress. Remember that we had written all these expressions in earlier lectures, I think lecture 2 or 3 or like at that time, and there we had derived this expression of this delta is the volume strain, and from that we had obtained this, right. We had obtained all this, and then we have also obtained the expression for lambda by lambda plus 2 mu by 3 means this quantity by this. So, we had done all that. So, for an incompressible material, therefore, this xx is written as, okay, after you substitute all that, it will be minus p plus 2 mu, it will be E of xx, and then yy similarly is equal to minus p plus 2 mu E yy, and zz will be minus p plus 2 mu u zz. So, we derived, okay, all these things, and also we can write here therefore, xz and yzx, this is equal to 2 mu exz, okay, like that. So, we had derived all that, and so what I will do today is or in the next class, that we will use these expressions and we will find out derive the expression for this particular thin film, okay, from considering that it is an incompressible material to begin with. So, it is just to the way that we will derive will be similar to the one that we did, and so basically we should get back the consistent results, right, at the end. So, we will show that we do get that. So, the reason that I am putting it, I am presenting it is because in many practical problems, okay, the compressibility of the film is not there. So, you can consider that adhesive as an incompressible material, and so you can directly use this expression and derive these equations and solve the problems. Okay. So, I will take it up in the next lecture. Thank you.